Now let's look around the solar system at some of the worlds where life might exist and look at how they stack up based on the major criteria we've just discussed. We'll start with the easy one, the Earth. We know that Earth has organic materials on its surface and in its oceans. As we mentioned earlier, most of these were probably originally brought to the Earth from the outer solar system by comets and asteroids. There is abundant sunlight at the Earth's surface. We've also seen that some of the life on Earth uses the planet's internal heat as an energy source. The Earth also has abundant liquid water on its surface. In addition, the Earth's atmosphere and surface show considerable evidence of modification by living organisms, including the presence of over 20% free oxygen in the atmosphere and large parts of the land surface covered with signs of vegetation. Also, on the night side of the Earth, we can see cities lit up by artificial lighting. So our conclusion is that there is in fact life here on the Earth, and you shouldn't be surprised if you find some here.
For a long time, people have speculated about life on Mars. Mars is the only world other than the Earth that is close to the habitable zone, and it has many other similarities to Earth. There is considerable question about whether or not organic materials exist on Mars. There have been some reports of trace amounts of methane, the simplest organic compound in the Martian atmosphere, but other measurements suggest that there is no methane there. The surface and atmosphere of Mars are difficult places for organic molecules, since Mars offers no protection from the sun's ultraviolet light. However, there's still a chance that these could be present under the surface. The obvious energy source on Mars is sunlight at the surface, which is about half as bright as on Earth. There's a small amount of internal heat in Mars, but much less than on Earth. There's probably liquid water on Mars, but it's entirely underground, except for rare, brief flows at the surface. Liquid water isn't stable on the Martian surface because there's so little atmosphere. So Mars looks like a difficult environment for life to exist, though there's still a chance that it could exist there underground in some simple form. However, in the past, Mars looked a lot more promising. The atmosphere was thicker, there was liquid water on the surface, and the interior of the planet was much hotter, giving more opportunity for the planet's internal heat to act as an energy source. In fact, at the time when life was forming on Earth, 3.5 to 4 billion years ago, Mars looked a lot more Earth-like than it does today. So it may be that the best we can hope for from Mars would be some sign of fossils, like the ancient stromatolites we see in the Earth's early history. In fact, much of the exploration of Mars has been designed to look for the sorts of environments where life might have flourished in this early period in the planet's history.
Jupiter's moon Europa is the most promising of the outer solar system moons that might have the conditions for life, but it's not the only one. Some of the others that have many similarities include Jupiter's Ganymede and Saturn's Enceladus. As a world in the outer solar system, Europa has plenty of access to organic materials. Every comet that hits it brings in a new supply of complex carbon molecules, and the low temperatures in this part of the solar system mean that these compounds have a good chance of remaining intact. In the outer solar system, sunlight becomes a difficult energy source to use. The intensity of sunlight at Europa is only 1/25th as much as on Earth, and further out in the solar system, it gets even worse. However, Europa has plenty of internal heating produced by tides from Jupiter. In fact, many scientists think that there are as many active volcanoes on Europa as on its neighbor Io. We can't see them, though, because they're at the bottom of a 100-kilometer deep ocean of liquid water, just below the frozen surface we see here. These deep oceans exist because of all that tidal heating. As we said earlier, there's more liquid water in Europa than in all of the Earth's oceans. Finally, when we look at Europa, we see patches of darker material in the ice. We don't know what this dark stuff is. Most scientists think it's either organic material brought in by impacts or rocky material brought up by Europa's volcanoes. However, one of the most speculative ideas is that this is evidence of life within the oceans themselves. So Europa is considered by many scientists to be the best place outside of the Earth to look for life in our solar system. It really seems to have all of the conditions needed for life to begin and flourish. And there are some plans being developed to try to land on Europa and try to determine what is happening in the oceans under the ice.
Now let's look at a less likely option, Saturn's moon Titan. We know that Titan has the raw materials needed for life. There are complex organics in its atmosphere and all over the surface. There's likely some internal heating on Titan. In addition, sunlight can act as an energy source here, though in a way that is different from what we see on Earth. As we've seen, methane in Titan's atmosphere reacts with sunlight to produce complex organic compounds. Many of these carry enough chemical potential energy that if they're consumed by living organisms on the surface, this could act as an energy-rich food for those organisms. Liquid water is not an option on Titan's surface. It's far too cold. Though like Europa, there is probably liquid water below the surface. However, at the surface we see lakes of liquid ethane and methane, cycling in and out of the atmosphere like the water cycle on Earth. If there's any way for these to act as a medium for the chemistry of life, this is where it would happen. The trick here is that it's very cold, only 90 Kelvin at the surface of Titan. In fact, Titan has been described as having a chemical environment very much like what the early Earth had, but put into a deep freeze. We have no idea if life is possible under these conditions. So we have to consider Titan as, at best, a dark horse candidate for life. There's a lot that is promising, but far too many unknowns to be able to say if there's any chance here or not.
The largest Jovian planets have also been suggested as possible homes for life. Here the living organisms would have to be floating in the dense atmosphere. Certainly Jupiter and Saturn have abundant raw materials. There are organics in both of their atmospheres, and the brownish haze we see on Saturn is made of complex carbon molecules similar to what we see in Titan's atmosphere. Internal heat is very important on these two worlds, providing much of the energy that powers the strong winds. Sunlight may also be important, though as we saw for Europa, the sun provides a lot less energy than we get here on Earth. There is liquid water in the lowest layers of clouds of these worlds. The upper clouds are made of ammonia, and some of this may also be in the form of liquid droplets. However, the biggest problem with these worlds is the stability of conditions. Anything floating in a Jovian atmosphere is going to be subject to very strong convective winds. These winds carry anything in them up to high cold altitudes and then drop down into the much hotter lower atmosphere. It seems unlikely that any sort of self-replicating molecule would be able to survive a few cycles of this sort of treatment. So as a result, most scientists don't consider the atmosphere of these planets to be very promising. We should probably consider them to be very unlikely candidates for life.
We've just been looking at life in our own solar system, but we should keep in mind that the solar system is just one star out of the 100 billion stars that make up our galaxy, never mind the many other galaxies out there. So let's finish up by thinking about a much bigger question. How common is life in the larger universe? Until and unless we actually find direct evidence of life elsewhere in the universe, the main way we can tackle this question is by figuring out how easy it is for life to get started. Does it happen on any world that has the right general conditions? Or is it something extremely unlikely, even when everything looks right about a world? Here, knowing about life in our solar system may tell us the answer. If we find life on Europa or one of the other watery Jovian moons, or something growing in the ethane lakes of Titan, or even fossils of ancient life on Mars, then we can be pretty confident that life is very common in the universe as a whole. We've already seen that our sun is not unusual in having many large and small worlds going around it. So if life can get started 2 or more times here, then it must be easy for life to start whenever the conditions are right. So probably there are billions of worlds with life in our galaxy. On the other hand, if there is no life in any of the Jovian moons, and no sign that it ever developed on Mars or Europa or anywhere else but Earth, then we can say that it's not enough to just set up the right general conditions. Life is much more unlikely even when everything looks good. So then it may be that life is quite rare in the larger universe. Either way, it's likely that the exploration of our own solar system will help us understand what the chances are of ever finding life beyond it.
Here's a your turn question. Look over your own mystery solar system and see if any of the terrestrial planets look like promising homes for life. You'll have to look at things like the real surface temperature, not just the no greenhouse temperature, whether there's evidence of an atmosphere, and anything else that might suggest life could or couldn't exist there. Make sure you explain what works and or doesn't work about each of the terrestrial planets.
We've reached the end of this planetary astronomy course. This is a good time to look back at some of the big underlying themes of the class. The first theme has been the connection between the sciences. You signed up for an astronomy course, but what you've seen is that astronomy is tied up with physics, chemistry, geology, atmospheric science, and even biology, and they all have to fit together into a coherent whole. After all, labels like physics and chemistry are things humans invented. There's nothing in nature that says this is where physics ends and chemistry begins. So if we want to understand real processes in the universe, we have to use all of the available tools.
The next theme is process. Science is not just about knowing a bunch of gee-whiz facts. Throughout this course, we've seen that what scientists are really interested in is how things work. Not just that a planet has craters and mountains on it, but why those craters and mountains are there. It's an understanding of the process that allows us to make predictions, and it's those predictions that test our understanding of the universe. One thing an understanding of process gives us is an appreciation of how the different parts of science fit together. When we look at something like a set of mountains here on Earth, we can see them as the result of plate motions on the Earth's surface. But these motions are driven by the planet's internal heat, which comes from the radioactive elements the Earth accreted when it formed. The Earth has lots of these elements because it formed in the warm inner solar system where ices weren't able to condense. So all the Earth could form from were the rock and metal. The same mountains are being eroded by the actions of the planet's atmosphere, which is produced by the outgassing of greenhouse gases that have since been modified by life. These gases were also brought to the Earth through the collisions of comets during the cleanup phase of solar system formation. All of these major processes that operate on worlds can be seen in the history of a set of mountains on the Earth.
The final theme here is the one that brings most people into this class: general education. Most people who take this course are not planning to become astronomy majors or even science majors. Instead, they're here to fill a general education requirement for their degree or transfer. If you're one of those students, you may be wondering why it is that you have to take a science course when your major is business or history or music or some other field. In fact, the reason for this is very old. It goes back 1,000 years, and it says that when you get a degree, you haven't just learned about a particular field of study. Instead, getting a degree means you become an educated member of the society, someone who's been exposed to many different fields of learning and many different ways of viewing the world. So in this course, if you developed a better understanding of how scientists view the world, what sorts of problems they find interesting, and how they go about trying to solve them, and even better, if you can use this way of thinking in the rest of your life, then you've achieved one of the major goals of this course. That concludes Planetary Astronomy. Best of luck on the final exam.